All right, good morning, everyone, and I hope you all are staying healthy and warm out on this cold November day. Welcome to the final session of the Georgia Tech Manufacturing Institute's Fall 22 Lunch and Learn Lecture Series. My name is Dr. Billy Brown. I'm Senior Research Faculty and Education Workforce Development Director for GTMI. I encourage you guys to please spread the word, and as we continue to grow our audience and network, which provides value for the GTMI community. And before I introduce today's speaker, I will first introduce GTMI, provide some brief instructions for the audience. GTMI is one of 11 Georgia Tech interdisciplinary research institutes that uniquely focuses on manufacturing research, development, and deployment. We help tackle the grand challenges of today's manufacturers and assist partners in moving innovations from the lab to the market. GTMI has a wide variety of facilities for basic research on main campus, as well as nearby on 14th Street for more applied research on our advanced manufacturing pilot facility. GTMI's mission includes education and workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. GTMI hosts the Lunch and Learn series each semester. These sessions are excellent opportunities for Georgia Tech faculty, undergraduate, graduate level students, and researchers, as well as a global manufacturing community to learn and share advanced manufacturing knowledge. Today is our final lecture for this fall, so I'm glad everyone showed up a little bit early today. We are both in person and streaming online via Zoom. We want today's session to be interactive, so please put your questions in the chat window if you're online, or if you're here in person, go ahead and jot them down so the speaker can address them at the end of the presentation. Today's lecture will not be long, as the speaker is planning to wrap up close to noon actually today. She has to teach a class following the lecture. So today I'm pleased to introduce Dr. Akanksha Menon, who will discuss composite materials for energy efficient buildings. Dr. Menon is an assistant professor in the Woodruff School of Mechanical Engineering at Georgia Tech and directs the Water Energy Research Lab. Prior to this, she was an ITRI Rosenfeld postdoctoral fellow in the energy technologies area at Lawrence Berkeley National Laboratory, where she continues to be a research affiliate. Her research group focuses on applying thermal science engineering and functional materials to develop sustainable technologies for water energy nexus. Examples include solar desalination for circular water economy, thermal energy storage for decarbonization of heat, and carbon negative building materials. Dr. Menon received her PhD in mechanical engineering from Georgia Tech, where she developed polymer-based thermoelectric materials and devices for energy harvesting and personal thermal regulation. Dr. Menon is a recipient of the 2019 Sigma Psi Dissertation Award and the 2017 Materials Research Society Silver Award. She was also recognized in the 2020 Falling Walls Breakthrough of the Year, Emerging Talents category, where she was featured by the U.S. Department of Energy and their Women in Energy initiative. Dr. Menon is in the class of 1969 Teaching Fellows cohort and currently serves as the faculty advisor for Pi Tau Sigma Mechanical Engineering Honor Society. So in today's presentation, Dr. Menon will discuss making buildings green by integrating renewable energy generation with thermal energy storage through the use of thermochemical building materials, which is attractive in buildings where space is limited. Further, Dr. Menon will discuss how wood-based composites can serve as both a structural and thermal insulation material for buildings while sequestering carbon. Overall, her lecture will elucidate how composite materials can be engineered to achieve desired structural and thermal properties to lower the energy and carbon footprint of the buildings sector. Dr. Menon, you may begin your presentation.
Thank you so much for the introduction, and good afternoon, everyone. Thank you for being here. Sorry we had to shift this a little bit earlier because I teach right after this. So today's presentation we'll really just focus on what we're doing in building space, but I put together a few slides just to show you broadly the different things that my research group does. And so we work in the water energy space.
You can make it easier to
Yeah.
just use this, sure, right now.
Yes, you can make yeah.
Okay, here we go. Sorry for the technical difficulties.
All right, let's try that again. So we mainly work in the water energy space. And so the reason why this is the main, motivation area for our research group is because if you look at world electricity demand and project it over the next couple of decades, you see that we're still going to continue to be a very fossil fuel heavy economy, right? So we're still going to be very reliant on our fossil fuels, indicating that there's significant work that we still need to do to decarbonize energy. And then on the water side, if we look just by the end of this decade, so by 2030, of course, the global population is expected to increase. But what we notice is that about half that population is going to be experiencing severe water stress. And what that means is that we've withdrawn significant amounts of our naturally occurring freshwater reserves, and we have to figure out additional sources of clean water. And so water and energy are also very much interlinked. And so this is a Sankey chart that's from Lawrence Livermore National Lab. On the top half, you can see the different energy flows. So we can look at all of our different energy sources, again, primarily fossil-based. And then you can see it's being utilized in these different sectors of the economy. And at the end, some of that energy is utilized, it provides energy services, but about 60% is just dissipated. And it's primarily dissipated in the form of. And then on the bottom, we can look at the water flows. So here is all our different water sources, again, primarily freshwater sources, which used mainly for energy production. So for cooling our power plants, thermoelectric generation. Some water is used in the public sector, and then another significant portion is used for agriculture. And then if we follow water after it's used in these different sectors, see that about 70% of the water ends up being discharged, meaning that it's now used in the process, contaminated, and just discharged as wastewater. And so 60% of energy is dissipated as heat, 70% of water is discharged as wastewater. And so this is really why my group is focused on how do we recover and reuse the energy as well as the water, and how do we decarbonize very linear systems. And so just to understand how closely water and energy are linked, you may have heard this term, the energy-water nexus. So what that's really representing is that in the energy production process, a significant amount of water is required. So whether you're extracting your fuel, you're refining it, you're producing power, or you're cooling your power plant, across every step of the energy production process, water is a critical resource. So just as an example, in the oil and gas production process, typically to produce 1 barrel of oil, they use about 10 barrels of water, and that ends up getting contaminated and is just wastewater. And then on the flip side, if we look at how do we get water, notice that energy is one of the critical resources in order to get water. So whether we're extracting water from underground, whether we're purifying wastewater, or distributing it from a central facility, or if we're doing wastewater treatment, every step of the water cycle involves energy. And so this interlink between energy and water is what's referred to as the water energy nexus. And so any technology you develop in the energy space or in the water space, you need to keep this in mind and make sure you're not exacerbating the energy or water. So this is, broadly what my group focuses on. So we do a lot of desalination, water treatment, as well as on the energy side, which is mostly what I'll focus on in today's presentation. So here on the water side, we're looking at how can we integrate solar energy to produce clean water, and mainly using solar energy in the form of heat. And we're also looking at how can we get to zero liquid discharge. What this means is typically you just dump large amounts of wastewater. Instead, we use solar energy to treat the wastewater up until the point where we extract all the water, and then your salts precipitate out. So that's your zero liquid discharge. Then you're left with just solids, which could contain valuable resources. For example, lithium has become a very interesting material to try and get out of these desalination brines. And we do a lot of surface modification, making our heat transfer surfaces super hydrophobic or hydrophilic in order to be able to do this kind of performance. We also work with combination of membrane and thermal separations in order to get heat water. But for today's presentation, I'm going to focus on what we're doing in the energy space, primarily looking at the need for thermal energy storage, so storing energy as heat. And we'll look at mainly the buildings applications. In this case, the temperatures you need are under 100 degrees Celsius. And if we have time, I'll also discuss some of the work we're doing, collaborative work that we're doing on trying to decarbonize industrial heat, which then requires us to be at over 1,000 degrees Celsius. So it's a very challenging materials problem. We also do some work related to energy harvesting using thermoelectric materials. And then I'll also touch upon the work that we've just started with the Renewable Bioproducts Institute on designing carbon negative building materials. So not just thinking about the energy use in buildings, but also thinking about the actual materials that make up buildings, because there's a lot of embodied carbon in that. So linking, all of these topics is really thermal science and engineering, which is my background. And we're also using functional materials, so really leveraging materials that are thermally responsive in order to give us this energy efficient and water efficient behavior. So why do we care so much about heat, right? We've heard a lot more about we need electrification, we need electric vehicles, but we haven't heard so much on the heat side. But if you actually look at energy use, see the transportation sector accounts for about 30%, electricity is about 20%, and then there's this large chunk of energy use, so half the global energy use is really just in the form of heat. And this is primarily in the building sector, so residential and commercial buildings, in order to provide space heating, hot water, as well as in industrial processes. So in order to get to high temperatures, or really any range of temperatures, so it could range from about 50 degrees Celsius all the way up to 1,500 degrees Celsius for steel making and cement manufacturing. And why it's important to understand we need to decarbonize heat is because you look right now, 90% of our thermal energy is coming just from fossil fuels. And so we have to significantly be able to address this by decarbonizing our heat sources. So now if we look within the US, a residential building, and we look at all the different end uses in the building sector. And again, you see space heating plus the hot water makes up more than 2/3 of over 60% of the energy consumption in a building. And so this is really why we're focused on how can we do thermal energy storage as a means to meet these thermal demands in a building. So why not just do battery storage? Why do we have to do thermal storage, right? So now here we're looking at the electricity used in a building for space heating and water heating as a function of the hour of the day. And so you can see that space heating, there's this peak during the early hours of the day, and then water heating, there's a couple of different peaks. And we see where the solar generation, so the amount of solar energy produced is, maximum during the noon hours, but we see that that's offset from where the peak in demand is. And then if we see where electricity pricing is really high, notice that that's where we also have a high thermal demand. And so what this is telling us is that, yes, we can use renewable electrification in buildings in order to meet these demands, but oftentimes when the electricity is produced or the price of that electricity is offset from when that energy is required. And so to be able to match that demand with the renewable energy supply, we need storage. And sometimes you need that storage over a significantly longer duration, so over 8 hours. And batteries, lithium-ion batteries, are really not designed for doing this longer duration energy storage. And so that's why we're looking at thermal energy storage. You're storing energy as heat, and your end use is also in the form of heat. So we can think of these as just thermal batteries. And there's a few different options when we want to store energy as heat. We could just store it as sensible heat. So that is when you would just have a tank of hot water, heat it up, and store the energy in the tank until you need it. And so that's the simplest form of energy storage and pretty prominent in homes. Or you could do latent heat storage, so store that thermal energy in a phase change process. So the simplest example is melting ice. And in the building space, because this would happen, close to 0 degrees Celsius, so that's too low of a temperature for buildings. So a lot of people look at paraffin waxes, and these paraffin waxes have melting temperatures in that 20 to 40 degrees Celsius range, which matches building applications. And then the last category of storage is in a chemical reaction itself. So in a thermochemical reaction, and the heat of reaction is what stores and releases energy. And an example of that is the salt hydrates. So you have a salt with water molecules in the lattice. And if you apply the right temperature, you can essentially dehydrate the salt, so the water molecules leave as water vapor. And so these are these thermochemical reactions. Now, if we compare the three forms of energy storage, and let's say we want to store about 10 gigajoules of energy as heat, you notice immediately that if you use just sensible heating, you need a far larger volume of your tank compared to if you use a thermochemical reaction. And in a building, because space is one of the biggest constraints, you want to have the most compact solution in order to store a large amount of heat. And so that's why we focus on thermochemical reactions for thermal energy storage in buildings. And again, the idea is we're going to store the energy when it's available and then release that energy in the form of heat when it is required. And these thermochemical materials have the highest volumetric energy density among these different categories. And so that's why we're focused on using them for building applications. So what does this reaction look like? So essentially you start with your salt hydrate. You apply heat and that results in the endothermic reactions. You're providing energy, and you can think of that as charging our thermal battery, providing energy, and that ends up dehydrating the salt. So your water molecules leave, and you're left with the salt at a lower hydrated state. We can now run the reverse reaction when we want the energy. We will supply water molecules in the form of relative humidity or moisture, and the salt will take in that moisture, and that is an exothermic reaction. That's going to now release heat, which we will use for our building application. So this you can think of as the discharging of our thermal battery. So in a realistic system in a house, this is what the charging reaction would look like. We would use either solar energy as heat, or we would use low-cost grid electricity to joule heat our material. And when we joule heat our salt in this packed bed reactor, it's now going to undergo this endothermic charging reaction, and it maintains energy within this salt. And then when we want to extract that energy, we'll introduce moisture, so this relative humidity. And as your salt takes in that moisture, it's going to now undergo the exothermic reaction, which will give you heat at the temperatures that you would want for a building application. And so these salt hydrates that we work with are suitable for temperatures under 100 degrees Celsius. Because we're working in the building space. They're very low cost, so very common salts like calcium chloride is a thermochemical material. And they have these inherently high storage densities because, again, you're extracting the energy associated with these chemical bonds. The challenge, however, is in theory, yes, this is a nice reversible solid gas reaction, but in reality, that reaction reversibility really depends on the stability of the storage material. And so this is where there are a number of challenges that we're trying to address. For example, when we dehydrate our salt, so here's one of our salts, magnesium sulfate. As we dehydrate it, you notice that the salt pulverizes. So it breaks down into these much smaller structures. Or when we try to hydrate it, so here's the salt, and if you overhydrate it, you end up actually forming a salt solution. So now that's undesirable because we want the reaction to always be solid and gas. So we can either form a salt solution, or if you heat it at too high of a temperature, your salt can melt. And then you end up just forming this agglomerated block, and you lose the nice structure, microstructure of the salt itself. So as a result of this, what you notice is in the first cycle, because again, this is a thermal battery, so we're going to keep charging and discharging it. So each charge discharge corresponds to one cycle. And so at the beginning, our energy density, so the red is the heat of the reaction or the energy density. You notice that just over 20 cycles, that energy density has dropped to 60% of the initial value. So very quickly, you start losing the storage capacity of the material because of these instabilities in the material. If it pulverizes or forms these agglomerated blocks, when we put it into a packed bed, when we're flowing water vapor at a given temperature and relative humidity, and you have these compact blocks, you're not going to have heat and mass transport through the bed. And so because of that, your energy density, like I showed you, can drop significantly. The other factors that impact this is, so here's the salt structure itself. And so you can see the particle sizes can tend to be fairly large. And if we ball mill the salt, so this is strontium bromide, we can just ball mill the salt to create much larger surface area. And you can also see much more porosity in the structure once it's ball milled. So down to about 10 micron size particles, what we notice when we do thermogravimetric analysis is the ball mill salt, so shown here in the blue curve, ends up dehydrating much quicker than the pristine salt. More importantly, when we try to hydrate it, you can see that the hydration reaction is much quicker when we work with the ball milled salt rather than the pristine salt. And so the particle size has a significant impact on the kinetics of these reactions. And that directly ties in to the energy density itself. You can see our ball mill salts have energy densities over 600 joules per gram, whereas for the pristine salt, it's lower. And for some of our other salts, we see even bigger contrasts with and without ball milling. That really emphasizes the importance of understanding how the microstructure of the salt impacts the properties. So here's a list of the different salts that we work with. There's 6 different thermochemical salt hydrates. Again, some of these are very common materials like calcium chloride, magnesium chloride, and magnesium sulfate. And then there's the strontium salts, which tend to be much more stable, but also more expensive. And so we're trying to characterize those materials as well. So we can dehydrate them. So here's like a normalized extent of dehydration. So where 1 is the fully hydrated salt and 0 is the fully dehydrated or the anhydrous salt. And you can see for the different salts, out of the different salts, some of them tend to dehydrate very quickly, while some of these other ones like magnesium sulfate is very sluggish. It takes a long time for the magnesium sulfate to dehydrate. And this is just 100 milligrams of material. If you're working with grams and kilograms, these time scales can be even over several days. And so that's very undesirable. And a lot of that, again, is tied to the fact that some of these salts have this nice porous structure, whereas some other salts do not. And when we look at the hydration, so now we're providing moisture and the salt starts off in the dehydrated state, is picking up the moisture and goes up all the way to its fully hydrated state, 1. And again, you can see that these some of these salts like strontium bromide tends to pick up that moisture very quickly, whereas some of these other ones, again, the magnesium sulfate and this potassium carbonate are very sluggish in terms of how much moisture they pick up. And so we're focused on 2 approaches to try and address these inherent limitations that pristine salts have. In the first case, we're making salt mixtures. So we start with our pristine salt. We make a solution, so just a water solution of 1 salt and the second salt, mix the 2 solutions together, evaporate the water, and then ball mill it. And then we get this nice fine salt mixture. And then the second thing we're doing is we're making an organic-inorganic composite. So in this case, we have our salt solution, that's our inorganic material, and we work with hydrogels. This is our organic material, and we essentially just drip the hydrogel into the salt solution. Because these salts are divalent, it'll cross-link the hydrogel, and we can essentially encapsulate the salt. So the hydrogel forms this porous network, which holds the salt particles in place. So it's really just a scaffold. And here's an SEM image of some of the initial beads that we've made, and you can see the porous structure within this. In this case, it's an alginate hydrogel, and the salt is held within the bead. And so this, by physically holding the salt in place, it prevents it from breaking down, forming salt solution, and that really helps us get a much more stable material to work with, as well as introduces this porosity so that you can get fast kinetics during hydration and dehydration. So this is ongoing work. And switching gears a little bit, so what I talked about till now is the operational energy use in buildings. We want to provide energy for space heating and for hot water. But what about the embodied carbon or embodied energy in buildings, right? So if we look at CO2 emissions, again, just from building operations, so energy use, that's 27%, which we can decarbonize with thermal energy storage. But then the construction materials themselves also contribute significantly to the CO2 footprint. And the scary part is, again, by the end of this decade, that's expected to be about 60% of CO2 emissions just coming from the building sector, right? And a big part of it is tied to the materials that we use in our buildings. So for example, if we replace the steel that's used in construction with wood, we could cut the CO2 emissions by 15 to 30%. And so we really need to be able to switch to natural materials for the building, which can act as carbon sinks rather than carbon sources. And so this gives you an idea of how wood, as a natural material, can sequester a lot of carbon. So this is the forest carbon cycle. And wood also has some very attractive properties in order to be a building material. So if we look at the specific strength, we have to modify the wood, but you could get densified wood with a very high specific strength. And you can also get wood with a very low thermal conductivity, meaning it can be a very, very good insulator. And so what we're interested in is looking at how can we make wood into a structural and thermally insulating material for building applications. And so the way we can do that is with this building component referred to as a structural insulated panel, or SIP. So the SIP is a sandwich structure. You have two wood panels referred to as oriented strand boards. You can make these with just wood chips. And typically, if you use waste wood, that improves everything on a life cycle basis. And in between these wood boards, we sandwich a foam core. This is usually styrofoam, which again is petrochemically derived. And this structure, this SIP structure, can hold weight, so meaning that it's a structural material, but it can also act as your thermal insulation. So it serves two purposes for the building itself. However, because of how SIPs are currently made, even though it's using wood, the whole manufacturing process, the sourcing process, as well as the use of this styrofoam ends up making this SIP a carbon source rather than a carbon sink. And so our goal is to design these structural insulated panels with a high specific strength and low thermal conductivity, but also making sure on a life cycle basis that product is carbon negative, meaning that it's sequestering more carbon than is used to produce it. And so the way we do this is we have these waste wood chips. We add bio-based polymers as our adhesive rather than carcinogenic formaldehyde-based adhesives. And then we can hot press to form this rigid skin. So that's the top and bottom layer. And for the core, instead of working with styrofoam and other petroleum-based foam cores, we're actually working with natural fibers. So we work with wood fibers, which we can compress into these foam cores, and it can have comparable thermal insulation properties as the styrofoam. And so this is in collaboration with Professor Kaledzadu here in GTMI, as well as Georgia Pacific. So we get softwood chips from Georgia Pacific, and that's a waste from their lumber process, and we're using that waste to produce this SIP panel. And this is in, this work is actually funded by the Renewable Bioproducts Institute. So here's just some initial work that we've been doing. So again, these are softwood chips from Georgia Pacific that we sort. arranged into these layers. There's a few different orientations you can work with. So we're doing 0, 90, and 0. And again, this is just to get you the mechanical properties that you need. And then for the manufacturing process of it, we cold press the panel first and then hot press it at about 5 megapascals and 200 degrees Celsius in order to form these foam boards. And so right now we're just starting some tensile tests. So you can see the coupons. And we still need to modify this structure a little bit more in order to be able to meet these ASTM standards. So this is very much work that is ongoing. For the insulation, again, I told you currently it's this polystyrene type of closed cell insulation, meaning that it really cannot regulate relative humidity or moisture. And so a lot of times you can form mold on those surfaces. And so instead what we're looking at is natural fibers, which inherently have a hollow structure. And so, for example, wood fiber, kenaf fiber, hemp fiber, and this is hemp fiber from our lab. These are hollow materials, porous, and anisotropic, and all of those are exactly the properties we need in order to get to very low thermal conductivities. And in addition, the insulation material is open cell with these natural fibers, and so you can actually have your moisture go through the material. So it's vapor permeable, but at the same time, it's hydrophobic. So that really allows you to regulate the building environment much more. So very quickly then on the high temperature side, what we're doing is if we look at, so here's a list of some different industrial manufacturing processes and the temperatures required. And you can see that steel making, cement, glass melting, these processes require temperatures of over 1,000 degrees Celsius, and we just don't have a good energy source apart from burning fossil fuels right now. And so what we're looking at is, can we design high temperature thermal energy storage? So above 1,000 degrees Celsius, it has to be a low cost material, has to be electrically and thermally conductive in these ranges. It needs to be mechanically robust, needs to have a high energy density, and we should be able to cycle it so that we're providing heat to the process, taking in more heat and releasing heat. At these high temperatures, only a couple of material classes are options. And so you would have carbon or graphite. It does really well in some categories, but not so much in terms of its mechanical properties. There's also stability issues because graphite tends to sublimate as we go to these higher temperatures. Or we could work with ceramics. So ceramics do really well, and they're used as refractory materials in a lot of high temperature furnaces, but it doesn't have the required electrical or thermal properties to be used as high temperature thermal storage. So here the idea is, why not make a composite of graphite with these ceramics? And so here's some images of compressed ceramic with graphite powder. We work a lot with alumina as our ceramic and mixed in with graphite. We choose the amount of graphite in that composite so that we're getting electrical percolation and thermal percolation through the composite. And then what we do is we sinter it. So here's those pellets, which are sandwiched between two carbon heaters or two carbon strips. We pass electricity through the carbon strips. It joule heats to a temperature of about 1800 degrees Celsius, which then allows us to sinter these composites. And now this is what the grain structure of the sintered composite looks like. So we've significantly densified these pellets, and you can see these nice necks that have formed between these individual particles. And so we're using these high temperature composites and currently doing cycling studies. And this is in collaboration with Sean Lubner's group at Boston University, as well as with Lawrence Berkeley National Lab. So here again, ceramics allow us to get to a combination of properties between just graphite as well as ceramics. And so with that, thank you all for your time. And I just want to acknowledge my research group, as well as some of the initial funding and facilities that have been used for this work. And my contact information is here. Thank you, and I can take some questions.
Thank you very much. I think we have time for a couple questions.
This is not your expertise, but I saw something about sand batteries or sand storage, energy storage recently. I don't know.
Oh, yes.
Yeah.
So sand-based energy storage is, or even rocks. A lot of people are using rock-based energy storage. There again, you're really just storing it as sensible heat in the material, so you would need very large amounts of it.
I was curious about the salts. So how is that integrated, I guess, into building materials as far as?
So with the salts, so that's used for thermal energy storage. So we would put the salts into a packed bed, and you have air coming in. The air strips the heat from the exothermic chemical reaction, so you have hot air coming out. That hot air you would route for space heating or hot water.
Because I was curious if you could form a composite even with maybe the salts, as far as you know, with your later work. I don't know if that makes any sense, but your graphite ceramics, you know, if you could add salts to it, would that help what you're trying to do?
So there is some work on putting salts into like the building envelope itself, so the facade of buildings, and that's to do mostly, it is for energy storage, but that's mainly like phase change energy storage. So again, you can have these salts melt and then solidify again, and in that process it's storing and releasing heat. So that way you're using all this surface area of your buildings to actually store energy, and it's not directly reacting to the outside environment.
So we know Georgia has a pretty significant and robust timber industry,
That's right.
22 million acres or something. What are you doing to partner with them to do sustainable forestry? Obviously, there's nail laminated timber like we see in the Candida building. There's glue laminated material. There's mass timber. What sort of partnerships are you trying to create with the timber industry to encourage owners, architects, contractors to use more wood?
Right. So, I mean, right now our main collaboration is through Georgia Pacific, and Georgia Pacific sends us these wood chips. So they commercially make these oriented strand boards, and this is on the market. They send us this material from certified forests, and so these are sustainable forests. So we make sure that the material is coming. In that case, I think the way they set it up is that for every tree that you're chopping down, you have a certain number that you're regrowing. And so we make sure the wood that we start with is certified as sustainable. But beyond that, what we've learned from Georgia Pacific is that unless there are specific building codes to force the adoption of what would initially be more expensive materials, it becomes very challenging. And so right now there's a company in Maine which is really looking at reviving the forests in Maine, as well as the paper industry in Maine, and using old paper mills to do a lot of wood-based construction materials. But that's a very recent shift that's happened. So I think over the next few years, but honestly, a lot of these things have to be policy driven in order to motivate, especially companies, to take it up. So Georgia Pacific is happy to have us try out these things and de-risk it for them, but they cannot invest in it unless building codes force them to go that way.
Well, building codes are becoming more lenient to allow tall mass timber buildings.
Right.
So it's just the innovation on the design, professional side, and the willingness to take some risk on the owner side.
Right.
So don't move that needle.
Yeah, that's a harder one. We're much more on the technology side of things, but we're working with the civil and environmental engineering department here in order to do much more of these life cycle analyses and put that information at least out there for Georgia. And so that's why over here, I said this is something that we're trying to build here, but this is very much an effort that we've just gotten started.
How big would your network of packets have to be to like supply enough like heat to the building?
So that's the advantage with these thermochemical reactions, because you can see to store 10 gigajoules of energy. This is sufficient energy for several months. You only need about 2 cubic meters of volume. But again, this is assuming that your material works perfectly every time you're cycling it, right? But in reality, that's where you see a lot of losses. So you could end up at least needing to double this in order to get that reliable performance. So that's really what we're trying to address.
Did those, I guess they look like geodes, but it look containers for the salt particles. Did that help with the cycling performance?
It does. So we've done so these, right?
Mm-hmm.
Yeah, so these composite structures, because the salts are actually held in place, we've been able to cycle this about 70 cycles, and we've seen the performance does drop, but about 15% compared to 60% if you're working with just the salt by itself. So there is a significant advantage of trying to go this composite route.
All right, thank you very much. Yeah, thanks. We're gonna go ahead and end the session out of respect for your time, Dr. Menon. She has to teach a class, so we don't wanna.
I have a midterm for my class and they will freak out if I show up late, right? So I just want to make sure I'm there a few minutes early, but thank you all for coming.
Thank you so much. And right, we're gonna have her contact information at the end of the presentation. Here we go. So if you want to contact her, please do so offline. And I just want to thank everybody for participating in our lecture series. This again is our final lecture of the semester.
There's one question in the
Oh.
chat. One question in the chat. Can you take it? Question is, your wood-based composites. This is how it's written. Your wood-based composites, what are your thoughts on addressing moisture-related issues to prevent termite degradation?
Yeah, so that for sure is a challenge. And so we'll have to, well, there's flame retardants you have to use, as well as, so oftentimes waxes are also applied to the surface in order to regulate that moisture. You would have to do additional coatings on the surface depending on specific conditions.
All right, thank you so much. All right. We will have a spring series as far as to my knowledge. So just keep abreast, monitor our website, and we'll have an announcement come out sooner than later. So thank you. Take care.
Thank you, Billy.
I enjoyed that. That's good.